So you're remembering that anything begins with the letter C as a trig function has a minus sign in its derivative. Derivatives of tangents and cotangents have a square in their derivatives. Derivatives in secants and cosecants have themselves and their other function in their derivative. Remember all that? You need me to write the derivative rules down. You've got?
Or we're just tired.
Or both. Let's see if I can put them right here. Let's see. Derivative with respect to x of the sine of x is equal to the cosine of x. Derivative with respect to x of the cosine is minus the sine. Derivative with respect to x of a tangent is secant squared. I had to think on that one. Derivative with respect to x of a cotangent is a negative cosecant squared. Right? Secant and cosecant are buddies. And then the derivative with respect to x of secant has got itself in it and a cotangent in it. Oh, nope, secant tangent. Take that back. Secants are buddies with tangents. And the derivative with respect to x of a cosecant of x has itself in it. And that one has the cotangent. And then, quick, what's the derivative of e to the x?
E to the x.
Yay. And then the derivative of the natural log of x, 1 over x. So those are our new ones. We still have our old ones like the product rule and the quotient rule. So don't forget that. Give these a try. Let's see what happens to you.
No, actually, we have 3 marks.
Get honors?
That's lucky.
Chemistry usually has a couple 300 in it.
My biggest is my engineering class that has 42 kids.
That's pretty good. You're getting your money's worth. Let's take the derivative, don't simplify it, then we can compare and see if we're ready to go on or not. See if there's anything in that section I forgot to cover.
Do you ever want us to simplify it, or you'll specify it?
We're gonna need to start simplifying a little bit more so we can analyze the sign and stuff like that of the derivative. We're gonna need to use the derivative a lot more soon. Right now, we're just kind of getting the hang of doing it. No, I don't even have that on me. I got all that in the other notebook. We ready to check our answers? Chain rule problem. That one. So chain rule. Just bear with me. All right, well, let's check our answers. So here, we're going to do the product rule. Let's get in the habit of labeling our derivatives. So I'm going to do the first one times the derivative of the second. And again, up there, the derivative sign is just a positive cosine. Then the other way, the second times the derivative of the first. Typically, when I have trig functions involved, I put the derivative in the polynomial term in front. Now we move over here, copy down the 3. The derivative cosine gives me a minus sign, so that puts a plus here. Sine of x. So there's really nothing to simplify anyway. Simplify, so we get that one.
Right, so you added the 2x in front because of x squared.
Right, I'm doing the product rule. Derivative of the x squared plus 4 is a 2x.
Oh,
I just put it in front because that way I wouldn't have needed parentheses, but now I wasted the input with parentheses.
The reason you do it in that order, where you take the derivative of the second first and the derivative.
I've always done it that way, but remember what the product rule doesn't do. Always done that way ever since I was one. Yes, sir.
another question for the motion rule.
Uh-huh.
So you start off with, I believe you do f times 5 minus f prime times 2 prime.
Right,
Wow. Over g squared.
right.
What I was taught was always f prime times g minus.
Um,
Would that
It's this order. Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom square.
Okay, okay.
So I don't know which one was F and G. So
F is usually top.
this one has to be done in this order.
Okay,
Copy down the bottom, take the derivative of the top.
okay, it's usually I just flip the T with B, but still prime first, and then so it's just like 2 prime B minus
Okay, that's fine.
B
Right?
T,
Multiplication is commutative,
yeah.
so the order here doesn't matter.
Okay.
But this order matters. Okay, does that make sense? So let's do it. Let's take the derivative here. And let's label it. That's the name is G, so the derivative is G prime. Copy down the whole bottom. Secant of x plus the cosecant of x. And then the derivative of the top, the derivative tangent gives me the secant squared. The derivative of 1 is 0. Now copy it the other way. Copy down the top. And now the derivative of the bottom. So we encounter a secant. Its derivative is secant of x times the tangent of x. Plus, except for I'm going to need a minus right there, because I see a trig function that begins with a c, so the derivative will be a minus. Here the cosecant is minus cosecant of x, cotangent of x. And then all divided by the bottom squared. Again, there's no reason to simplify that. I don't think there's anything interesting going to come out of that. So far, so good? What'd you do to take the derivative here? What about the product rule? You see a product rule there? Good. There's the derivative using the product rule. Copy the first one down. And now I multiply by the derivative of the second one. So I put a 1 over x right here. Then the other way, copy the second one down. And then the derivative, the first one, 4 is a constant, derivative e to the x is e to the x. This derivative is going to change the sign here because I see a trig function with a c, so I'll get a plus. The cotangent has a cosecant squared. Yes, sir.
So it's similar to the first one, when I was looking at the product rule, do you not consider sine x minus 3 cosine x as like the second term of the product rule, and then x plus 4 as the first term? On the first
No,
example?
because this is one term here. Terms are separated by plus and minus signs.
So like you can't parentheses around both of those.
If I put parentheses, then what you're saying is correct, but there are no parentheses,
So you can't.
so
just
you
add-
read it from left to right,
Okay.
and it makes quite a difference. So without parentheses, that's one product. With parentheses, that's a different product. Okay. Let's look some more trig functions in our examples today. What we're going to do is to use the derivative to talk about instantaneous rates of change. Right now, our derivative measures the slope of the tangent line to a graph at a single point. So in section 3.4, we'll look at any instantaneous rate of change. So in all of these examples or in the discussion today, we're talking about a particle moving in the plane. So first we will just move it up and down a number line. Have an object that travels rectilinearly.
It's a word.
I know, and I said that out loud. It sounds like something Beavis and Butthead would laugh at.
Yeah.
There's a point moving along a number line, and so the position of that point will be measured as a function of time. Where it is on the number line is a function of time. And we want to know how far it travels over a time interval and what its average rate of change is over there, and what its instantaneous rate of change is over there. Suppose particle moves along a number line. Its position at time t is given by some function of t. Our number line. We've got our x coordinates here, but maybe at one time t, its position might be here. And then at another time t, its position might be here. Let's just call that f of t plus h. And so this distance in here, distance traveled on the time interval from time t to time t plus h. It's just the difference between those two. Terminal point minus initial point. And so the average rate of change, the average rate of change in position with respect to the change in time That's what it is in words. Here's what it is in notation. It's the change in position with respect to time. So it's this thing up here. And then the change in time is the difference between these two. T plus H minus T is just going to be H. For instance, if I drive to Dallas, it's about 360 miles. And suppose I average 60 miles per hour. That's 60 miles per hour. I bet it takes me probably 6 hours, right? So the change in position is 360 miles per hour. The elapsed time is 6 hours. And you get my 60 miles per hour as my average velocity, right? So that's what this is. It's an average velocity, change in position with respect to a change in time. You've probably driven to Dallas, you know you're not going 60 miles per hour hardly anywhere. Stopping at a few Dairy Queens, so that's changing your average velocity. You gotta get the big phone. Right, so sometimes you're stopped, sometimes you're moving, but the average velocity is just final position minus initial position divided by the elapsed time. That's what that is. Now, when you look at your speedometer at a certain instant, and it says you're doing maybe 82 miles per hour, that's the velocity at that particular instant. How do I make this average velocity into an instantaneous velocity? Shrink the time interval, right? So if the difference in time is 6 hours, well then whatever time here and time here, then the H represents the change in the time. Shrink the time interval down to an instant. We do that in calculus by taking this change to 0. So our instantaneous velocity or instantaneous rate of change involves taking the limit of that. The velocity at time t, it's going to be the limit as that increment in time goes to 0 of the change in position over the change in time. Or in our case, I used H to represent the change in time of this thing. But what is that called? What does that structure over here give us? That's just the derivative. It's the derivative of the position function. In general, the derivative of the position gives us the velocity. So the velocity at any time t is equal to the derivative of the position. What if I started with a velocity and I wanted to find an instantaneous rate of change in velocity? V of t plus h minus v of t divided by h. What's the instantaneous rate of change in velocity called?
Acceleration.
Acceleration. So v prime itself is going to be, so this is going to be f prime. And v prime itself is going to be the acceleration. That's time t.
Because it's the second derivative.
The derivative, second derivative position. Now, if I'm not talking about velocity, maybe I'm talking about a function that measures the temperature at a certain time of a city somewhere. then the derivative of the temperature would be the instantaneous rate of change in the temperature. Right? The second derivative will be how fast that temperature is changing, how fast that rate of change is changing. So we're not going to calculate the derivative with the definition anymore. We've got all these derivative rules. Let's look at this first example here. The particle moves along a number line so that its position at time t is given by S of t, typically position is denoted with the S instead of the F. S for position, V for velocity, and acceleration will be A.
S is position.
S is position. The state at time t. So minus t cubed plus 3t squared minus 3t, and my time interval is between 0 and 5 time units. We'll say it's seconds for now. And I want you to do this to this particular problem. In part A, determine the velocity and acceleration functions in part B. I want you to give intervals on which the particle is advancing and intervals on which it is retreating. How many of you have taken any physics? Then you know that velocity has a sign associated with it. So if the velocity is positive, the particle will be advancing. If velocity is negative, it will be retreating. Acceleration has a sign. If the acceleration is positive, then we consider the particle is accelerating. If the acceleration sign is negative, then it's said to be decelerating. So we'll do that next. Oh no, next we're going to find the whole distance traveled by this particle. And then we're going to find the speed and acceleration at each of the endpoints at 0 and at 5. What's the difference between speed and velocity? Are they the same thing? Speed is scalar, which means it's just a number, but also it's positive number, right? It's the thing that you see when you look down at your speedometer, whether you're advancing or retreating. So it's the absolute value of the velocity at that time. Okay, so we got a lot to do here. I'm going to erase all that junk over there so I've got room to do it. essentially what I wrote over here is that velocity is the first derivative of the position. The acceleration is the second derivative of the position. But we have to analyze the sign of it in order to answer the question in part B. So if you're ready, let's take the first two derivatives and label them as velocity and acceleration. Part A, velocity at any time t is the derivative of the position, which is helpful. Polynomial, so its derivative is pretty easy, negative 3t squared plus 6t minus 3. Then the acceleration function is the derivative of the velocity or the second derivative of the position. So I go up there and take the derivative of this thing, and we get negative 6t plus 6. Now, give intervals in which the particle is advancing and retreating. So we're talking about movement here. We need to see where the movement is positive and negative. So for part B, we need to know where the velocity is greater than 0 and less than 0. So the best way to figure that out is to find out where the velocity is equal to 0. Let's take this thing here, set it equal to 0, and see if we can find those values of t that make that 0. I'm going to factor out a negative 3, so there's, I get a polynomial, maybe I can factor from there. That's going to change the sign. Take negative 3 out of that, leaves me a negative 2. Take a negative 3 out of that, that leaves me a 1. So I need factors of 1 with the same sign that add to negative 2. Minus 1 squared. So the only place that this thing is stopped is when that factor is 0, and so that occurs when t is 1. So let's analyze the sign of the derivative in that time interval from 0 to 5. Here's t is equal to 1. And we want to know the sign of the velocity. That's easy. Now here it stopped. There's my velocity function in factored form. This part is always squared, so no matter what number I put in for t around 1, this is going to be a positive number. And then I'm going to multiply it by negative 3. So my velocity is always negative. That means it's never advancing. And it's retreating for all t other than 1. It's retreating on the interval from 0 to 1, and then again from 1 to 5. And I'm including those endpoints because when I put those two numbers in, I'll get a negative number. But when I put 1 in, I get 0. So let's get the total distance traveled. This object starts at time 0 somewhere on the number line, backs up until time 1, it stops, Then it starts up again and keeps backing up. Okay, so let's see where it is at each time. So for part C, it starts at time 0 on the number line at the origin. Okay, when t is 0, s is 0. When t is 1, let's figure out where it is when it stops its movement. It's at -1 to the third power plus 3 times 1 squared minus 3 times 1. So that's -1 plus 3 minus 3. It's at the x coordinate of -1, the position on the number line. And then at time 5, -5 cubed plus 3 times 5 squared minus 3 times 5. These are the position at each time. So -5 cubed is -125. 25 times 3 gives me plus 75, and then minus 15. So let's see, that's 140, a -140 plus 75, is that a -65? I think so. So here's what's happening. Starts off at the origin at time 0. Then it backs up to -1. And that's at time 1. Comes to a stop, but it doesn't turn around. And then it keeps going backwards until it hits -65. And that's at time 5. Yes, sir.
Which will always be the find it in absolute value since you always find the total distance traveled, but not the.
Right, I want a distance now, so I don't want negative numbers. So how long is this segment? And then this segment? There's done a total of 66 units. Well, this is just 64, right? From here to here. This is 1 unit. And this is 64 units. Right, between -1 and 65. So the total distance is 64 plus 1 or 65 units. No, I'll give you another example where there's a bit more movement on here. Because this thing never turned around. It just came to a stop and then kept going. So really looking at where it started and where it ended told me how far it moved. But we'll do one where it does some zigzag. Okay, so that's the total distance traveled, the speed and acceleration at the endpoints. So part D, speed is equal to the absolute value of the velocity at the given time. So at t is equal to 0, and at t is equal to 5, I go back to my velocity function, and I plug those numbers in here. So I've got a -3 times 0 squared plus 6 times 0 minus 3. That's a bunch of zeros there. The absolute value of 3 is 3. So that's 3 units per time. 3 distance units per time. And then V of 5 is -3 times 5 squared plus 6 times 5 minus 3. 25, that's a -75. Plus 30 is a -45, minus 3 is a -48. Pick the absolute value, 48 units of distance per time unit. Now we do the same thing with the acceleration. Acceleration at time 0, 0, 0. Acceleration is going to have a plus or minus associated with it. At time 0, what's my acceleration function? Right here. So it's going to be -6 times 0 plus 6. So it is positive, means it's accelerating as it's backing up. And at time 5, at -6 times 5 plus 6, so -30 plus 6 is a -24. So now it's decelerating as it's backing up.
So you only do the average speed.
Correct. Velocity and acceleration are signed entities
What do you mean sound?
as a plus or a minus. So in general, velocity greater than 0 means the object is advancing. Velocity less than 0 means the object is retreating. Acceleration greater than 0 means the object is accelerating. Acceleration less than 0 means the object is decelerating. Decelerate with 2 C's or 1 C? Should be 2, huh? The acceleration has 2. But that sure looks funny. Yeah, I'm going to go with what you said because you sounded pretty convinced. Just has 1. That looks a little bit better, but still looks funny. Okay, let's try the same thing, but with a different function. So keep the same questions. You will even keep the time interval. Let's go with 3t to the 4th minus 8t cubed minus 78t squared, double up the big numbers, plus 120t. This is going to be painful. Wednesdays are fair game for numbers. Mondays and Fridays, nah. Same instructions, bigger numbers. 3t to the 4th minus 8t cubed minus 78t squared plus 120t. About this off. Got it written down. Let's knock out the first 2 derivatives and label them as velocity and acceleration. Part A, velocity at time t is, let's tell you it's s prime. And then we get 12t cubed minus 24t squared. Um, 156. 156t plus 120. All right. Acceleration at time t is the second derivative. So we get 36t squared minus 48t minus 156. Are you happy with those? Now remember in part B, when we're looking at intervals in which it's advancing or retreating, we're looking at the change in sign of the velocity. So we first find the zeros, and then we'll look at what the sign is around the zeros. So for part B, we need to first find where velocity is 0. So I'm going to try to factor this thing. It's a third degree polynomial. Golly. Let's see if we've got any common factors in here. I'm going to hope that 12 is a common factor. I think I can pull out a 12. Let's see, 12 times 12 is 144. So 12 times 13 will give me the 156.
Prove that.
Yeah, then factor by grouping.
So we give up.
No, I say we go back to our algebra days. We have something called the rational root theorem.
Excuse me?
It says a polynomial, if a polynomial has any rational roots, rational means looks like a fraction or a whole number, then the rational roots take the form of factors of the last number divided by factors of the lead coefficient. So if this has rational roots, they take the form of either 1, 10, 2, 5 divided by 1. So possible rational factors. Possible rational roots are plus or minus 1, 10, 2, 5 divided by the roots of 1. So those are all just over 1. Remember our P's over Q's? Remember that, anybody?
It's been like 3 years since I took algebra.
You want to know how long it's been since I've taken algebra?
Probably longer than me.
Okay, so we can quickly check if 1 is a 0 by plugging 1 in for t. And if that adds to 0, then 1 is a 0. So if I put a 1 in here for those t's, I get a negative 15. That's a positive 11. T is equal to 1 is not a 0. Okay, I don't need to check if t is equal to negative 1 is a 0 because my time interval is between 0 and 5. So I can throw away the negative numbers. Not interested. Probably should check in case I want to factor it. So I want to see if t is equal to 2 is a 0, and I'm going to do that with synthetic division instead of plugging and chugging. I'm going to put a 2 right here, and I'm going to put the coefficients inside. I don't care about the 12. I got a 1, a negative 2, a negative 13, and a 10. Bring the 1 down. 2 times 1 is 2. That gives me a 0.
Wait. Aren't we choosing the positive numbers? Oh, wait.
Right.
never mind.
So I put the positive number out there. Okay, so 2 times 0 is 0. This gives me a negative 13. 2 times negative 13 is negative 26. I'm getting a number there, so 2 is not going to be a 0. Let's check if 5 is a 0. Bring the 1 down. 5 times 1 is 5. Add those together and give me 3. 3 times 5 is 15. Add those together and I get 2. 2 times 5 is 10. That gives me 20. So that's not a 0. It would add some promise, didn't it? And then let's check 10.
But it's on the interval.
Oh, yeah. Who cares about the 10? Well, in case I wanted to factor it, though.
So we give up. I feel like we've given it a good try.
Did you see Animal House?
No,
John Belushi talked about giving up.
who is that?
You don't know this one? Children, your assignment is go watch Animal House.
Isn't that a book too?
Was it a
No, that's
book?
Animal
No.
Farm.
Oh, okay.
Oh. What animal farm?
Those
You
ones that
really?
like communists and animals. Yeah.
Oh, yeah.
You guys are way too
Never-
educated.
never had to
No,
read
Animal Farm, but not Animal
You
House.
think I read?
I'm gonna have to beat you back down.
Wait a second,
But you still would have heard of it.
But John Belushi said, did we give up when the Germans bombed Pearl Harbor?
Yes.
So we came back at them. And we freaking say yes. We came with a force.
Okay, I don't know why my thingy didn't factor, because I thought like problems factored for me. Let me make sure I copied it down right.
Oh, so was he done the show?
Oh, I want a plus sign here.
Oh.
So we fixed that problem. Look, it's done.
Oh, so we get to assume it's solved now.
Yeah, so that's gonna give me a plus right here
Dog.
and a plus right there. And a plus right there and there. And so one of these is probably gonna work. So the moral of the story is don't give up, change the problem. So we're gonna go back and make that plus. First, let me check the one. Uh-oh, look, one is gonna be a 0. 1 plus 2 plus 10 is 13 minus 13. T is equal to 1 is a 0. So let's find the other factor. All right, so this factors as, so my velocity factors, I've got the 12 still here, t minus 1. This becomes 1t squared plus 3t minus 10. Now, are there any factors of a negative 10, opposite in sign, that add to positive 3? 5 and 2, right? So that factors again. So I want a t plus 5 and a t minus 2. We got it completely factored. How rewarding is that? Now remember, we're saying the velocity equal to 0. So velocity is 0 when t is 1, negative 5, and 2. And we don't care about this one because it's not in our time. Now we're going to analyze the sign of the velocity on the number line between 0 and 5 with stopping points at 1 and 2. So the velocity is 0 here, the velocity is 0 there, and we want the sign of the velocity in between. So I'm looking at it in its factored form so that I don't have to plug and chug too hard. I'm going to pick numbers from each interval, and I'm going to plug them into the factors, multiply together, and decide whether I have a positive or negative number. Like if I put a 1/2 in for t, 1/2 minus 1 is negative. 1/2 plus 5 is positive. 1/2 minus 2 is negative. Of course, the 12 is positive. Multiply those three together, and what kind of sign will you get?
Oh,
Positive. Now let's do it again. Let's take 1/2 and plug it in for t. So 1/2 minus 1 is positive. 1/2 plus 5 is positive, but 1/2 minus 2 is negative. Now let's plug a 3 in for t. That'll be positive, positive, positive. So it advances, it retreats, and then it advances. Advances.
Are you just, you're just arbitrarily putting in different numbers? Or
I'm
like
picking numbers in between.
in between
Whatever
each-
it does at one of them, it does at all of them. Okay, so it advances on the interval from 0 to 1. Doesn't do anything at 1, it stopped there. And then it advances again from 2 to 5. And it retreats. for the velocity is negative, and that's between 1 and 2. To figure the total distance traveled, we have to figure out where it is on the number line at each of those times. So we're going to need to plug those numbers into the position as well as 0 and 5.
What was your third number? Did you use 2.5?
Just any number between 2 and 5. Any old number at all between 2 and 5. What's the matter?
Sorry about that.
Oh.
So can you explain in between 1 and 2 why it's decelerating?
Because I got a negative velocity. I didn't say decelerating, I said retreating.
Retreating.
The negative velocity means it's retreating.
But how did you get the negative if you did?
I'm putting in, say, negative 1.5. Negative 1.5, I'm sorry, positive 1.5. 1.5 minus 1 is a positive number. 1.5 plus 5 is a positive number. But 1.5 minus 2 is a negative number. Positive times a positive times a negative is negative. All right, so let's figure out its position on each of those and diagram its movement, and then figure the total distance traveled. So I'm going to plug numbers into here. I need to make some room. And so I think I will erase from, where can I erase? I guess I'll erase from here. So let's figure out, so we need position at time 0, at time 5, and that adds 2 stopping points. We need those 4 positions. So S of 0 is equal to 0, 0, 0, 0, 0.
This is part C.
Yes. S of 5 is 3 times 5 to the 4th is 625. 5 cubed is 125. 5 squared is 25. And then 5 times 120. All right, how about a little help on that one? We've got a calculator for me. I'm not doing that.
How do you want to use those?
You're not, just use it right now, real quick. You don't want to watch me do public arithmetic.
1,095?
I just want the whole shebang. Is that the 1,095?
No, it's not. It's much lower.
I got S of 0 real quick. While you're doing that, I'm gonna get S of 1. S of 1 is 3 plus 8 minus 78 plus 120. So 128, 131 minus 78. $53.
I think it's 4,645.
I'm gonna trust you on that one. Numbers aren't important. And then S of 2. Three times 2 to the 4th is going to be 3 times 16 plus 8 times 8 minus 78 times 4 plus 240. That's 48. That's 64. That's 312. 240, 64, 48. 40. All right, we've got all of our positions then. We make a diagram as to what's going on. different number line. At time 0, we're at 0. From time 0 to time 1, we moved over to 53. From time 1 to time 2, we moved back to 40. And from time 2 to time 5, we moved over to 4,645.
Roughly.
Roughly. So we need to add the lengths of those line segments together.
God.
This line segment is 53 units long. This line segment is 13 units long. And this line segment is 4,605 units long. How did I get those numbers?
Because it's the difference between the two points.
That's right. So I'm finding in distance traveled, the important numbers were the two stopping points and the end points. So if I put them in order, and who cares which one's bigger, I'll put them in absolute value. S of 0 minus S of 1 plus S of 1 minus next stopping point was a 2 plus, and I went from 2 to 5. S of 2 minus S of 5. Find the difference between them and throw away the sign. So here's where the 53 comes in, then the 13, and then the 4,605. So the total distance traveled is the sum of those. That is 66 added to 4,005. And 4, 6, 7, 1 units.
Roughly.
Roughly.
Yeah, something happened in the last calculation. I think it's correct, but
I don't think anything happened. I think that's a good number. Mighty fine number. It's the idea that matters. So you find the stopping points, find the position at each stopping point, and then take the difference incrementally. Keep it in absolute value. So that gives us the total distance traveled. Let's find the speed and acceleration at time 0 and at time 5. And I've erased my velocity and acceleration functions. Guess I have to crank them out real quick. So my velocity function at time t was 12t cubed plus 24t squared minus, what was this again? 156t plus 120. Acceleration at time t was 36t squared plus 48t minus 156. So to get this, the speed at time 0 is the magnitude of the velocity. So v of 0 is 120. Velocity at time 5
big numbers.
is this number. I'm gonna leave it there. The acceleration at time 0 is a negative 156. I'm going here. The acceleration at time 5 is 36 times 25 plus 48 times 5 minus 156. So let's move our particle now off the number line. Let's make a particle move in the plane. Maybe you know from physics that if an article, a particle, not an article, is thrown either from ground level or from a certain height, it follows the path of the parabola. And the things that make it follow the path of the parabola is the initial velocity and the effect of gravity. Right? So we're going to look at that. So if an object is thrown with an initial velocity,
Are you done with the example?
yep, of v0 from an initial height of h0 feet. This velocity is going to be in feet per second. Then from physics, we know that height of the object at any time t is given by an upside down parabola. It looks like this. Its height at time t is equal to the effect of gravity. It's going to be pulling downward, so I'm going to make it minus g t squared plus v0 times t plus h0. If we're in feet, the effect of gravity, I think I want to that. Yeah, I want a negative 1/2 in there. Yes.
So I was doing the web work yesterday, and a problem like this popped up,
Uh-huh.
and it gives you some very not nice numbers. So can we use a calculator to calculate those, or how do you want us to do that? 'Cause on the exams.
Yeah. I mean, how nice is not nice? You had fractional values for t and
It
stuff
was
like that.
like, no, I'm saying like the final values of like, I'm trying to think.
Right? If
was
I'm
like-
going to test, you could do this. Just stop like I did. You can do that on web work
Okay,
too.
well,
You just,
there was like one question was asking like, what is the time whenever the like object hits the ground, and I
you had to use a quadratic formula.
yeah, but would you just leave it as in like in the quadratic formula?
Yeah, that would work.
Okay.
That would work. Okay, so if we're in feet and seconds, then G is given by 32 feet per second per second. So if I put that in there now, our formula looks like the height at any time t is negative 16 t squared plus v0 t plus h0. So the diagram is this. You've got some initial height of h0. The object is thrown or shot up, and then it eventually lands. And so the height at any time t, here's our t-axis. The height at any time t is given by h of t. If it follows the path of a parabola, there's going to be somewhere that it hits its peak and turns around. So what do we know? How do we know where it hits its turnaround point? Velocity is 0. And we know that it lands when its height is 0. And we know the initial height is that when time is 0.
That's much.
Good markers today.
How do you get the buy markers?
I don't buy them. This is your tuition dollars at work.
Awesome.
We have a supply cabinet guarded. They don't just let us rummage through the supply cabinet. We have to say, please go
Do they like
on.
train on it, get rid of them before they give them to you?
No, we leave them laying around the
Wait,
classroom.
do they- Is there a Marshall system?
The Marshall
You know
system,
what I'm talking about?
they throw me against the floor and put me for taking too many staples.
No, like, it's like armed, like, teachers.
Oh, I don't know.
You know
I'm
what
sure
I'm
we
talking
have plenty of armed teachers.
Okay.
We got the gun loving kind. You know, you can't bring it in
about?
campus.
In high school, they-
Well, what aren't schools? Depends on the issue. Yeah,
I can't remember. Can you conceal on campus?
No, you can't bring weapons on campus.
Usually like certain teachers.
What
Like,
if
you
you're
leave it in your truck.
lawsuit after lawsuit after lawsuit after lawsuit?
Yeah, you can leave it in your truck or you can, most of the dorms have a gun case. If you need to bring one on campus, they put you in a gun case. Okay, we got time for quickly evaluating something here. Let's quickly do this. Okay, in this example, a dynamite blast blows a heavy rock straight up. With a launch velocity of 160 feet per second. It reaches a height of h of t is equal to negative 16 t squared plus 160 t after t seconds. So this rock was sitting on the ground. They stuck a stick of dynamite underneath it, and it flew up in the air, and it's going to come down. Here's the initial velocity. There's the effective gravity. I don't have a constant term, so that means my initial height is 0. It starts out at ground level. So I want to know, how high does this rock go? That's probably all we got time for today. Put some other stuff in it next time. All right, so look at my little picture with my red ink. To figure out the very maximum height, we have to find where the velocity is 0. The time that makes the velocity 0 will generate the maximum height. Good? So we need the velocity. So find the time when velocity is 0. Velocity is the derivative of the position. Yes, sir.
Just the position.
This is the position. Height at any time t is the position. So the velocity is the derivative of the position. So in our example, it's negative 32t plus 160. Now we're setting 0 in for the velocity, and you're going to solve this equation for t. Move the 32t over, divide 160 by 32, and I believe that's 5. Takes 5 seconds to reach its maximum height, and now we find its maximum height by doing what? Plug it in where?
The original.
The height. So the height when t is equal to 5 is negative 16 times 5 squared plus 160 times 5. Let's see, 5 times 16 is 90. So this is going to be 900 on the end. Let's see, 20 times 16 is a negative 320. 5 times 16 is a 90. So that's a negative 410. So negative 410 plus 900. 480 feet is the maximum height. Yes. Where am I looking? 16 times 25. Where do I get 410? 2 times 16 is 32. 5 times 16 is 90. 80. That was close.
Sorry, we were on the same. On the same thing.
How about 500 then?
Yeah.
500 feet is the maximum height? Yes. Okay, say it again. Oh crap, there I did it again. Okay, so we're getting closer. It was the rush. It was the rush. I was trying to get you out here in time. 2 mistakes cost us 2 minutes. Okay, we'll do some more of these examples next time, but that might be enough to get you started on doing some of this stuff.
What?
To come in here when you got all this stuff going on.
I also realize how much I love this class.
I'm zooming. If you need to love it from the home comfort of your home. I don't want you to be miserable in this Arctic environment in here.
And then I got like 4 of them. Give me strong medication. It's just not getting better.
Maybe some of the stronger medication.
I think you just need some others. Beth, how many times do you think you've left class?
Y'all good? Do you have any questions at home, Nathan? Thank you. Took me a while, but the final answer to that last example was 400.
So, like, you help somebody.